The bet was an encyclopedia. That is what Stephen Hawking handed to John Preskill in Dublin in 2004, in front of a room full of physicists as payment for a wager he had lost, not a metaphorical encyclopedia, an actual physical book. Because Preskill had argued for years that information survives a black hole, that it has to survive, that quantum mechanics absolutely requires it. And Hawking had argued the opposite. And now, after 30 years, Hawking was standing in front of the room admitting he had been wrong. The encyclopedia was a joke. The point was not. Because what Hawking had been defending for those 30 years was a conclusion that, if true, would mean quantum mechanics as we understand it is not just incomplete. It would mean quantum mechanics is broken at a structural level. And quantum mechanics has never made a single incorrect experimental prediction. Not one. In the entire history of its application, every calculation about atoms, about photons, about the behavior of matter at scales smaller than anything you can see, it has been right every single time someone bothered to check. So something was wrong somewhere, and figuring out exactly where took most of a generation of theoretical physicists. It starts in 1974. Hawking was 32 years old, already confined to a wheelchair, already losing his voice. And he produced a calculation that connected quantum mechanics and general relativity in a way nobody had managed before. The calculation showed that black holes are not perfectly black. They radiate, they emit particles from just outside the event horizon through a quantum process. Particle-antiparticle pairs forming near the boundary, one particle escaping outward and one falling in, the black hole losing a tiny fraction of its mass in each exchange. Over time, truly vast time, longer than anything we have a useful name for, a black hole radiates completely away. It evaporates, it disappears. The temperature of this radiation depends on the black hole's mass. The formula is clean. The physics is elegant, and almost everyone who read it agreed it was probably right. The problem was what followed from it. Hawking's radiation is thermal. It has a temperature, it has a spectrum, and the spectrum is the same regardless of what fell into the black hole. Throw in an encyclopedia, throw in a single hydrogen atom, throw in a quantum system carrying specific, irreducible information about its physical state. The radiation that comes out is identical in all three cases. Statistically identical. The radiation does not know what formed the black hole. It carries no signature. It is, in the precise technical sense, random. And when the black hole finishes evaporating, when there is nothing left, not even a remnant, that information is gone, not scrambled, not hidden in correlations too subtle to read, gone, destroyed, as if it never crossed the horizon. This is the information paradox, and Hawking was not troubled by it. His position was explicit. General relativity wins at the event horizon. The horizon is absolute. Nothing that crosses it can influence the outside. Therefore, the outgoing radiation cannot carry information about what fell in. Therefore, information is lost. And if quantum mechanics says this is impossible, then quantum mechanics must break down in the presence of strong enough gravity. He said this in papers, he said it at conferences, he placed bets on it for 30 years. Leonard Susskind disagreed. This is, and I am choosing the word carefully, an understatement. Susskind did not merely hold a different view. He spent the better part of 2 decades arguing that Hawking's position was not a bold claim about the limits of quantum mechanics. It was a flat violation of one of its most foundational structural principles, unitarity. The rule that the evolution of any quantum system is reversible in principle. That information cannot be destroyed. That the past is always recoverable from the present state of a system, at least in principle, even if the recovery is impossibly complex in practice. Susskind's argument was essentially this: you do not get to decide that unitarity breaks down because your calculation is more convenient that way. Unitarity is not a guideline. It is a structural pillar. Remove it, and quantum mechanics does not become approximate or limited in some domain. It becomes internally inconsistent. It stops being a coherent theory. The exchanges between them were not collegial. Susskind later wrote a book about it, The Black Hole War, 2008, and he describes the dynamic with a controlled intensity that makes clear he thought Hawking was not just wrong, but wrong in a way that was bad for physics. And that deference to reputation was making the community slower than it should have been to push back. He was explicit, he was persistent, he was right. But the core difficulty was that neither side had the decisive tool to force a resolution. Hawking had a calculation. Susskind had a principle. The calculation and the principle contradicted each other. And in physics, when that happens, the question is always, which one have we gotten wrong? The first serious structural challenge to Hawking's position came from Susskind and Gerard Hooft in the early 1990s through a framework called black hole complementarity. The idea grew from a careful examination of what the event horizon looks like from 2 genuinely different reference frames, and what it means that they cannot, even in principle, compare observations. Here is the thought experiment. You are watching from outside a black hole as someone falls in. From your perspective, due to extreme gravitational time dilation near the horizon, they appear to slow down as they approach. Their clock runs slower relative to yours. In the extreme limit, they appear to asymptotically approach the boundary but never quite cross it. Not in any reasonable amount of time, not in the lifetime of the universe, not from your vantage point. Meanwhile, Hawking radiation leaks out from near that same boundary. The infalling person's quantum state gets absorbed into the dynamics near the horizon and slowly scrambled into the outgoing radiation. Beyond any practical recovery, but technically present, the information is in there somewhere. From your infalling friend's own perspective, none of this happens. They cross the horizon without incident. The equivalence principle, Einstein's foundational insight that freefall is the natural state that you cannot locally distinguish between gravity and acceleration guarantees that crossing an event horizon should feel like nothing at all if tidal forces are small. They pass through, they continue inward, and eventually they reach the singularity. Complementarity says both descriptions are correct. Information is absorbed and re-radiated from the outside perspective. The infalling observer experiences smooth space-time. There is no contradiction because no single observer ever witnesses both things simultaneously. The outside observer and the infalling observer cannot exchange information once the infalling observer has crossed the boundary. Both are self-consistent. Neither one is privileged. Hawking did not find this persuasive. His response, roughly, was that complementarity was a bookkeeping arrangement, not a physical resolution. The radiation is still thermal. The information is still not recoverable from it in any meaningful sense because the correlations required to encode it are simply not there. The outside observer sees radiation, but they cannot read anything from it about what fell in because the information was not written into the outgoing particles in the first place. And then in 1997, the ground shifted, not loudly. A paper appeared, authored by a 29-year-old physicist named Juan Maldacena, titled in the dry technical style that high-energy physics favors for papers that turn out to reorient everything. The paper established a correspondence, a duality, a precise mathematical equivalence between two physically different looking theories. On one side, a full theory of gravity in a particular curved space-time called anti-de Sitter space. A negatively curved universe with a boundary, not quite our universe, but a consistent mathematical one. On the other, a quantum field theory with no gravity at all, living on the lower dimensional boundary of that space-time. Like a hologram, in a specific technical sense, three-dimensional gravitational physics exactly encoded in two-dimensional quantum mechanics. The correspondence is exact, not approximate, not valid in certain limits, exact. Every physical process describable on the gravitational side has a precise translation into the boundary theory. They are the same physics written in two languages, and the boundary theory is an ordinary quantum mechanical system, which means it evolves unitarily, which means information is preserved, not as an additional assumption, but as a mathematical consequence of the equivalence itself. If you throw something into a black hole on the gravitational side, the boundary theory already contains the answer to what happens to the information. And the answer is that it survives. It has to. The dynamics of the boundary theory require it. This was not a direct proof that information is preserved in our universe. Anti-de Sitter space has a negative cosmological constant and a boundary. Our universe does not. The correspondence applies to that specific setting, but it destroyed the general position that information loss is a natural or acceptable feature of quantum gravity, because here was a concrete, mathematically exact example, not a toy model, not a hand-waving argument of quantum gravity, and information was preserved in it. Demonstrably, And the structural reason it was preserved was not specific to the geometry. It was unitarity, which applies everywhere quantum mechanics applies. If you wanted to continue arguing that information is lost in physical black holes in our universe, you would need to explain why our universe differs from anti-de Sitter space in a way that specifically permits information destruction when ADIS does not. That turned out to be an argument nobody could construct convincingly. Hawking spent several years after 1997 working through his own response. He had a technical objection, an argument involving the gravitational path integral summing over different space-time topologies, which he thought might allow information loss even within a unitary-looking framework because of contributions from exotic space-time geometries. He and Malcolm Perry worked on this for years. By 2004, working through the path integral more carefully, he had convinced himself that his original 1974 derivation had relied on treating the black hole geometry as fixed and classical, a background approximation that fails in precisely the regime where information loss would actually manifest. A more careful treatment, summing over all possible space-time histories, gives back a unitary answer. The information survives. His own calculation had been wrong, not because the radiation does not exist, but because the approximations baked into the derivation broke down in a way he had not originally accounted for. He stood up in Dublin and said so. He paid the bet. He handed over the encyclopedia, which Prescal accepted, apparently somewhat reluctantly, noting that a burned encyclopedia would have been a more apt price, since theoretically you could reconstruct it from the ash. That was the point. In principle, recoverable. That is all unitarity requires. And in physics, this is treated as intellectual strength. Not failure, the argument moved toward truth. That is what matters. But, and here is what the clean version of the story leaves out entirely. In 2012, 4 physicists, Ahmed Amhiri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that reopened everything. The AMPS paper, named from their initials, what it showed is that the resolution everyone had settled into, complementarity, unitarity, information preserved in radiation, carries inside it a new contradiction, a sharper one, more targeted, aimed at the very center of the framework. The argument is precise. For information to escape in the Hawking radiation, the outgoing particles must be entangled with the early radiation, the radiation that left the black hole long ago in its history. This is not an optional feature. It is required by unitarity. The late outgoing radiation carries information about what fell in. Information lives in quantum correlations. Quantum correlations require entanglement between the late radiation and the early radiation. But quantum mechanics contains a theorem about entanglement called monogamy. One particle cannot be maximally entangled with 2 separate systems simultaneously. If the outgoing Hawking particle is maximally entangled with the early radiation, as unitarity demands, it cannot also be entangled with its partner just inside the horizon. And the entanglement with the interior partner is exactly what produces smooth space-time at the horizon. It is the mechanism by which the infalling observer experiences nothing at the boundary. It is how the vacuum state at the horizon is the ordinary vacuum. Break that entanglement and the vacuum is not smooth. The infalling observer does not cross through empty space. They hit something, a wall of intense high energy radiation, a firewall. So complementarity, the resolution that said both pictures are correct as long as no single observer can witness both simultaneously, turns out to be insufficient. Because if unitarity is genuinely preserved in the outgoing radiation, the entanglement required to preserve it breaks the entanglement that produces a smooth horizon. You cannot have both unitarity or smooth horizon. One of them fails. The physics community's reaction to AMPS was difficult to describe charitably without using words like panic, which I am using descriptively, not pejoratively, because within months, hundreds of papers appeared attempting responses. Some argued that the monogamy constraint could be evaded. Some argued that the interior of the black hole is somehow not an independent system from the exterior in the way the argument assumes. Some argued that complementarity needs to be extended or modified in a specific way. Some proposed that the firewall is real and that the equivalence principle breaks down at the horizon in a way we had not previously considered. Hawking himself, in the last years before his death in 2018, returned to the problem. The soft hair papers, the 2016 paper with Perry and Strominger, and the longer companion paper completed just before he died, proposed a mechanism. Soft hair, low energy photons, and gravitons associated with the symmetries of the horizon, called supertranslations, leave an imprint when particles fall in. The infalling information is recorded in these soft quanta on the horizon. The outgoing radiation can, in principle, be correlated with this imprint. The information escapes not through dramatic firewall dynamics, but through a subtle encoding in the hair. Whether soft hair resolves the paradox is still, right now, an open question. The honest answer is that most physicists working on the problem think soft hair captures something real about the structure of horizons. The idea that black holes have far richer quantum structure near the boundary than the classical no-hair theorem suggested, but that it does not on its own fully close the information paradox. The firewall argument still stands in modified form. The mechanism is not yet fully written down. What Hawking's 30-year error and the argument against it actually produced is something stranger and in some ways more significant than a simple resolved debate. It produced a reorientation of what theoretical physics thinks gravity is. A growing conviction held by Maldacena and Susskind and a substantial fraction of the community working at the boundary of these fields. That space-time geometry is not fundamental, that it emerges from something more basic, and that something more basic is quantum information. The Bekenstein-Hawking formula, which Hawking derived, says the entropy of a black hole is proportional to the area of its horizon, not the volume, measured in units of the Planck area. Entropy, in the information theoretic sense, counts bits. The area of the horizon counts bits. The holographic principle that followed from this says the maximum information content of any region of space scales with its surface area rather than its volume. Three-dimensional space carries no more information than its two-dimensional boundary can encode. Hawking's calculation produced that formula. The argument against him produced a framework that explains why it is true. The geometry of space-time encodes quantum information on a boundary. Curvature is information. The structure of space and time may be a derived description of something more fundamental. An entanglement structure in a quantum system that does not itself have geometry. He did not live to see a resolution. The soft hair papers point towards something. The firewall question remains open. Nobody has written a complete microscopic account of exactly how the information in a collapsing star ends up encoded in Hawking radiation that leaks. Out over 10 to the power of 67 years, for a solar mass black hole, that is the evaporation timescale. And it is not a number that means anything in human terms. It is longer than anything. And we cannot test any of this experimentally. The Hawking temperature of a solar mass black hole is approximately 60 nanokelvin above absolute zero, far colder than the cosmic microwave background. No instrument exists or will exist to detect it directly. So we have mathematics that says information is preserved. We have mathematics that says preserving it requires either a firewall or something else we have not yet identified. And we have a gap between those two conclusions that nobody has bridged. Hawking conceded in 2004. The argument that forced the concession was 20 years in the building and rested on a mathematical structure, ads/CFT, that nobody anticipated and that one 29-year-old produced in a single paper. The argument that followed the concession arrived 8 years later and has been running for over a decade with no settled resolution. He was wrong for 30 years about information loss. The case against him did not close the question. It cracked it open wider and revealed that what was underneath was not a simpler problem, but a deeper one. What information is, what the horizon actually is, whether space-time geometry is real or emergent, how quantum mechanics and gravity actually fit together at the level of mechanism, not just in a formal duality that tells us the answer without showing the working. That is where the question sits now, not with an answer, with a direction towards something that nobody, not Susskind, not Maldacena, not Hawking in the final years when he was still working on it, has yet fully seen.